recording. Oh God, I look terrible too. That's great. Anyways.
Don't look bad.
So I apologize in advance, you guys. My brain is complete garbage, which some of you have talked to me in the last week or so probably already know. So I will probably drift in and out, and you guys are probably going to have to help me out. And if I make a mistake, please call me out. So the first thing I wanted to go through was just looking at the practice exam and kind of highlighting some of the stuff that you should definitely be able to do. So we'll go through that, and then I figure we can do some some practice problems together from the practice exam via the camera. Does that make sense, guys? Cool. All right, so first things first, units. Right, so number one is all about, do you know what different units are? That is absolutely a question that you will have on this exam, right? So, and it's not limited to these, right? It's not limited to volume, pressure, temperature, or amount of gas. It could be density, molarity, molar mass, pretty much any unit, okay? So you should be able to look at a quantity and know what the unit is. Does that make sense? Cool. Any questions about that? Cool. And again, there's variations on these. So, you know, I have liters here for a volume, but that's not the only way that you can see a volume, right? There's also cubic centimeters, right? M cubed. So just being aware of the fact that there's all of these different units, right? Just being able to categorize them, right? Any other questions about that one? Cool. I'm probably not going to ask you one like this because we didn't go through it in lecture, or if it is in the lectures from before, I don't remember. So, so this is more of an exercise in, do you understand how the ideal gas law works? Meaning, if you hold something constant, what happens to another variable? So this kind of question probably won't be on there, but it's helpful in terms of understanding the relationship between variables in the ideal gas law. These kinds of conversions you absolutely need to do. They'll probably be in the context of another problem, right? So they'll be in the context of either a simple gas law problem or a two-state problem, possibly a gas stoichiometry problem. Does that make sense? So all conversions on board. You do not need to know the conversion factors, right? So they're not given here, but they will be given on the exam, okay? Everybody with me on that? So conversion factors going from, like, say, ATM to millimeters of mercury, Celsius to Kelvin, all of that will be given. PV equals nRT will be given. So the only thing you need to do is know how to do those conversions, okay? Everybody comfortable with that?
Yeah, if you're going to give us kind of like a conversion table of the basics, right?
I am, exactly,
We
yeah.
have to know how to actually work them.
Yes, exactly. So I'll have anything that requires them will have like a little picture of all of the possible variables and conversions you might need.
Okay, thank you for
That
that.
includes the R, so the 0.08206 number.
Absolutely, with the units, yes.
Okay. Thank you for that.
Yes, thank you for pointing that out. The gas constant will absolutely be there. But I'm guessing at this point you guys probably remember those, but the pressure of remembering them on a test, I don't want to stress you guys out. So yeah, for sure. So those will be there. Okay, so any other questions about up through number 4? We're all right? Okay, so I don't want to solve these problems yet, but I do kind of want to talk about looking at a problem and knowing what kind of problem it is, right? Because I think that's one of the things that that students struggle with on this exam, because there's so many different kinds of problems, right? So looking at this problem, what kind of problem is this? So first of all, we have three basic types of equations, right? We have gas, molarity, and stoichiometry, and a mixture of the three, right? So what is this one of those three?
Just a simple gas problem because we
Yeah,
were
that's what I was
given the
going.
3 variables and asked for the 4th.
Yeah.
Exactly. So this problem number 5 is a simple gas law problem. And you know that because you're given 3 out of the 4 variables in your PV equals nRT equation, right? And again, there's 5 letters here, right? But one of them is not a variable. Which one?
N.
R?
R. R, right? So R is a constant. That's the gas constant. So you have P, V, N, and T are your possible variables, right? Here you're given a pressure, a temperature, and a number of moles, right? So you would be looking for V. That's a simple gas law problem, right? Now, one of the most important things to remember when you're doing any gas law problem is that there's one particular unit that you're always going to have to convert.
Celsius to Kelvin.
Celsius to Kelvin, right? Everybody okay with that?
Mhm.
So 100% of gas law problems require that you convert Celsius into Kelvin before
Right.
you do the problem, right? If you're dealing with a simple gas law problem, you may have to do other conversions as well. If you're dealing with a two-state problem, you probably only have to convert Celsius, right? And we'll talk about that in just a second. Any other questions about this one? We're okay. So I don't think there are any two-state questions on this, but there will definitely be one on the exam, okay? So how would you identify a problem that's a two-state gas law problem? What would you be looking for? So in this problem, we were given 3 out of the 4 variables, right? And we were asked for the 4th. What is different about the two-state problems?
You'll have like 2 different temperatures or 2 different pressures or something.
Yeah. So you'll be given an initial and a final condition, right? For one of the variables at least. So you'll have 2 of one of the variables. Does that make sense, guys? So
Mhm.
here I have 1 pressure, 1 temperature, 1 moles, right? In a two-state problem, I would have 2 of one of these. Does that make sense?
Mhm.
Everybody with me? So if you see 2 of the same kind of variable, that should be an indication that you have a two-state problem, right? Another indication is usually the words initial and new or final conditions will be used in the problem, right? Questions about that?
Okay.
For those ones, do we just have to go from one to another? So we do like the ratio for the 2-step ones?
So we'll do an example of a two-state problem in just a second. But the two-state problems, generally you're looking for whatever the variables are you want on one side of your ideal gas law, and whatever's constant, meaning the ones that aren't given, are going to go on the other side. And then you set the variables that are changing equal to each other. We'll go through a problem like that. Yeah. Any other questions about gas law? We're all right for now. Cool. All right, so then this problem here is, so first of all, we're given a volume, a temperature, oops, and a pressure, right? So what should we be thinking we're probably going to use in this problem?
Permanent.
Yeah, we're going to need the ideal gas law, right? Pervnert. Everybody with me there? So you've never seen pressure given in a problem that you didn't need the ideal gas law for, right? So if you see a pressure, that's a good indication that you're going to need PV equals nRT, right? Does that make sense? Same with temperature, right? There's no reason to give temperature in a reaction that doesn't involve PV equals nRT.
Okay.
Cool?
Yeah. So if we see both of either one of those, a pressure or a temperature put in a problem, we know just to go straight to that. Okay.
Right. We're thinking that we're going to need to use that. That may not be the first step, right? That may not be where we start in the problem, but we're thinking we're going to need to use PV equals nRT. Okay.
Okay.
So now for the rest of the question, right, we're looking at a reaction. So I know that I need PV equals nRT, but I also have a chemical reaction given, right? So what kind of gas problem should I be thinking this is?
Stoichiometry.
Gas stoichiometry, right? Everybody comfortable with that? Cool. So gas stoichiometry problems generally are going to have one of two types of formats, right? Either you're going to have some mass or volume and concentration of reactant, right? And you're going to be going to moles of product and then to your PV equals nRT, right? So that's one type of problem where you're given the mass or the volume, the concentration of a reactant. You need to find the moles of the product and then use that in your Pervnert equation, right? The other way, which is what we have here, is we're starting off with needing to use PV equals nRT to find moles, right? And then once we have moles, we can convert to moles of, looks like reactant, yeah. So here we're looking for moles of reactant and then grams of reactant, right? So it's basically just going backwards. Does that make sense?
Mhm.
So we've had problems before where you saw mass and volume and concentration, and then going to moles and then going to the PV equals nRT. Those were on the solutions quiz, I believe, right? But this is just going the opposite direction, right? So same type of problem, but here we're starting with Pervnert to find the moles, right? And then we'll go to the moles of the reactant, which in this case, we're looking for magnesium and then grams of magnesium. Does that make sense, guys?
Mhm.
Cool. And we'll go through how to do this problem again in just a little bit, but I just wanted to talk about the general forms that you could see for gas stoichiometry. Cool,
And
Z?
you had mentioned that you'll always have a balanced equation for us, right?
That's correct. Yes, you'll always have a balanced chemical equation given. Yeah.
Danica, this is a little off topic of this question, but there was no tie-nye questions on the exam review. Do you think we'll have them on our quiz or our exam?
There will be, yes, but they won't be. So the way that you guys saw them on the quiz, I just asked you to basically do the tie and the nye, right?
Mhm.
The way that you'll see them on the exam will be like pieces of a tie and an eye. So it'll be like, what's the how many of these ions would be formed in the tie for this reaction, right? Or like I literally just did these problems and I don't remember what they are. What else? What else? Oh, looking at like what the spectators might be.
Okay, so you would
Right.
ask us like, who are the spectators in this?
Yes, exactly. Right. Or does this reaction have a net ionic equation? If so, what is it? You know, of these choices, right?
Okay,
So along those lines, it's not going to be like having to do out all of those steps, right?
okay. So you're kind of giving it to us and then we have to decide which one is the proper.
Exactly. Yeah. So hopefully a less time consuming version of those problems, right? Okay. Any other questions about tie and nye?
Once you get the flow of tie of night, it's kind of cool.
It's not too bad, right?
Yeah, once you kind of get the flow of it and realize what it is, it's like, oh, okay.
Just breaking stuff up.
Mm-hmm.
I like it because you get to get rid of things. I love canceling things. Maybe that's why I like dimensional analysis so much. I'm like, get out of here, units. Bye. Cool. I'm very cool. Anyways. All right.
I have a quick question. I thought that like some other review session, you said that there were 3 types of stoichiometry problems, but you just wrote 2.
So there's general stoichiometry, and then there's solution and gas, right? So they're not really different because you could have mixtures of all 3 of them, right? But when I talk about general stoichiometry, I'm talking about just mass to mass. Does that make sense? So no polarities, no gas loss step. Does that make sense? Does that translate?
I think so. I'm just in my mind. I'm trying to think if there's any other kinds that were not on the practice exam, because for some reason I remember like the lab problems to be a lot harder, but maybe it's just that I didn't know how to do them.
I think that's it. I think that it's mainly because when you first did those problems, you weren't as versed in this as you are now.
Yeah.
And again, the more of these you do, the more you're like, oh, this is not so bad. Which brings up another really important point, which is that the number one thing that students will do wrong on this exam is they will make problems harder than they need to be. Okay. So I've primed you guys with a million really difficult questions, which you guys have risen to the occasion of, which is awesome and I love it. But not all questions have to be complicated, right? So just because you've done these more complicated problems doesn't mean that every problem is that version, right? So that's what we're trying to go through today, is so that you understand when to use what techniques and when you can just say, oh, this is a pretty easy problem, and attack it like that, not be like, oh my god, this is way too easy, it must be wrong, right? Because that's definitely the thing that will get you into hot water on this exam. So
I have a question about that.
yeah.
When to recognize when to use the M1 V1 equals M2 V2? Are you going to have questions like that?
So that's a dilution equation, right? So you would literally have the words dilution or diluted in the problem, right? And you would also not be dealing with a chemical reaction. So M1 V1 equals M2 V2 is only used for dilutions and only when you don't have a chemical reaction. Thank you. That was a good question, Nikki.
Yeah,
And don't the ratios have to be 1-to-1?
They do, but I don't teach it like that because then you have to be able to think through another step in terms of the logic. So I very simply just say if it's not a delusion, don't do it, right? Because it's better safe than sorry. Does that make sense?
Mm-hmm.
If you're very comfortable understanding when the ratios are 1-to-1 molar ratio wise, then obviously you're welcome to use that technique. But I personally think that you have dimensional analysis, much better to use a tool that you're comfortable with, that you're familiar with, that works all the time, right? Other question? Doing okay? Katie, did you have a question too? Or was that it?
No, I was just kind of telling Nikki I have a really hard time figuring when I use N1, V1.
Yeah, so literally if you don't see the word dilute or dilution or diluted in there somewhere, don't use it. Yeah. Any other questions? Cool. Okay, so you're from chapter 8, and it's been like a million years since we ended chapter 8, or since we're at the beginning of chapter 8 anyways. There's a couple of things that I want you to be comfortable with, right? You're not going to need to draw Lewis structures. We're done with that. At least if you don't have to take the final, you're done with that. If you have to take the final, you're probably going to see them again. But what I do want you to be comfortable with is this idea of how to tell whether or not something is polar or non-polar, right? And what intermolecular forces might be present and how those intermolecular forces tell you about the phase or the state of the compound or molecule you're looking at, right? So for example, water is a liquid, right? Everybody's comfortable with that.
Yeah.
Why is water a liquid? Why isn't it a gas at room temperature?
Because it's,
Hydrogen bonds?
Yeah, hydrogen bonds, right? Got those real strong dipole-dipole hydrogen bonds. That's what keeps it stuck together in a condensed phase, right? So what phase would you expect oxygen to be in?
Gas.
gas.
Yes. Yeah. Why? I mean, besides the fact that you breathe it, right?
Because it has dispersion forces.
It only has dispersion forces, right? Does that make sense, guys?
Mhm.
Is everybody comfortable with that? Cool.
How do we know if something has dipole-dipole, what state it's going to be in?
Dipole-dipole and hydrogen bonding, you would assume are going to be liquids. So generally speaking, if I was going to give you a solid example, it would be a very obvious solid, like an ionic solid. So like sodium chloride,
Mm.
something that you're literally familiar with, right?
Mm.
So it's more about the difference between liquids and gases, right? Because it's more common to have liquids with dipole and hydrogen bonds. Is everybody with me on that?
Mhm.
Cool. Beep, boop, beep. When you get into liquids, right, we talk about different liquids and how they mix. So when we're talking about solutions, we say that polar solvents like to mix with other polar compounds, right? Oil is an example of a polar or non-polar?
Non-polar.
Or
Non-polar, right? So would something like sodium chloride dissolve in oil?
I'm gonna say no.
No, right? So sodium chloride is ionic, right? So it's going to want to dissolve in polar solvents.
Mhm.
Example of a polar solvent would be
Water?
water. Exactly. Yeah. Does that make sense, guys?
Yes. I had to go back in my brain, but yes.
No worries. That's okay. Is everybody kind of comfortable with those? Ish. Cool.
Most part.
Cool. Any questions about that material? Cool. All right. So number 10, we have a molarity problem, right? Now, is this a simple molarity problem or a titration or a stoichiometry problem?
Simple?
Simple, right?
Simple, yeah.
Everybody comfortable with why?
Presta atención. Ah, ok.
No lo
Ah.
jales, solamente muérdelo. Vete por mi sopa y corre.
Solo una más.
Some people. Okay. So here we're given a volume and a molarity, right? And we're asked to find the mass. So this is a simple molarity problem, and we'll talk about how to do those in just a little bit. Everybody comfortable with how we determined that this is a simple molarity problem?
Because of what we're given, because we're given the
So first of all, you're not, excuse me, you're not given a chemical reaction, right? So it's definitely not a stoichiometry problem.
yeah.
You don't see the word dilution in here at all,
No.
right? And you're only given one volume and one molarity, right?
Yeah.
So those would be all of your keys to why this is a simple molarity problem, not a dilution, not a titration. Okay. Okay. So number 11, what kind of problem are we thinking this one is?
Off the top of my head, I say straight.
Solution stoichiometry, right?
Can you give me what the definition of stoichiometry is? I don't like you keep saying it. I don't really know what that is.
Stoichiometry is the fancy word for the coefficients that are out here.
Okay.
So it's basically how many of each ingredient, right?
Cool.
When we have stoichiometry problems, we're literally talking about how to go from ingredients to products, right?
Gotcha. That makes sense.
Yeah. So you'll never have a stoichiometry problem that doesn't have a balanced chemical equation, right? So you're always going to have a BCE in a stoichiometry problem. Cool. Great question. I'm sure you are not alone in wondering that.
No, I could barely pronounce it, let alone what it
Yeah, it's the $25 word that no matter how many times I define it for you guys, it'll still be like, what is this?
What?
Weird. Yeah, totally.
We've been doing it for so long. I was like almost embarrassed to ask, but I was like,
and please don't be. I completely understand. It's one of those words that's so weird that especially too, because if you wrote it down when you were looking at the lecture, maybe you might have remembered it, but I don't know about you guys, but one of the things that's most challenging for me in learning new words or new names or anything like that is I have to see it. Like I have to visually see how it's spelled in order for me to like piece it together. And if I haven't done that, then there's no way it's sticking to my brain, right? So it could be that I've been saying this word that whole time and you're literally just like, it's just a fucking bunch of string of letters. I don't know what it means. It's space to me. So yeah. So anyways, on that note.
That's why they say to make a relation when you meet somebody, you have to make like a visual relation to it and you'll remember the person's name.
Like entry, right? Stoichiometry. Coefficients, did I spell that right? Whatever, it's close enough. It's close enough. Close enough for a Friday. Anyone else have questions about that? Thank you for asking that, Sadie. Cool. All right. So now we have the pH scale is used to express
concentration of hydrogen ions.
That's right. Concentration of hydrogen ions in solution, right? Everybody with me there? Cool. These other pieces of information are tangential, right? They have to do with solutions in general, but they're not pieces of information that we could get from the pH, right? Does that make sense? Everybody picking up what I'm laying down there? So the only piece of information that we get from the pH directly is the concentration of hydrogen ions. Okay, so number 13, you'll definitely see a problem like this. I think there was some of this on the lab, the acid-base lab as well. Oh, and the acid-base quiz, right? Acid-base quiz. Yeah, Jesse, what's up?
I have a question about the number 12. So I remember in that chemistry video crash course, it was saying that H3O is the same, or you can call it H plus, but does it go the opposite direction?
Yes.
Like,
the H plus and the hydronium ion, which is the H3O plus.
like how is that the same thing?
Because in water, H plus doesn't ever exist by itself. It always sticks to a water molecule, right? When it sticks to a water molecule, that's when you get H3O plus. Does that make sense, Jesse?
Yeah, okay, I didn't even realize that. Thank you. But it might not always be in water?
No, it will always be in water. Acid-base chemistry 100% of the time is in water.
Okay, thank you.
Right? So they mean the same thing. I tend to just use H plus, but certainly it's good to know both. Yeah, acid-base chemistry, I'm trying to think of an example where this isn't true and it's not necessarily my area, but I'm going to go ahead and go out and say that there is no acid-base chemistry outside of aqueous environments. So there may be things like acid-base relationships, but they're not the same. Okay. And one of the reasons for that is because water is so good at sticking to that hydrogen ion. So that H plus and water really like to stick together. They're pretty happy together. So so that's one of the reasons why that's the only medium that I can think of off the top of my head that does acid-base chemistry. It's water. Organic chemists might disagree with me on that. There might be exceptions, but I would say generally speaking, it's pretty true. Any other questions about stuff? Cool. Okay. So definitely number 13, something like this will be on the exam. So if we have a solution that starts at a pH of 6 and it goes to a pH of 9, the solution has become
Less acidic,
it's become less acidic,
more basic.
also become more basic.
Okay.
Right? So anytime you're moving from a lower pH to a higher pH, right? You are increasing alkalinity or basicity, and you are decreasing acidity. Does that make sense, guys? Anytime you're going from a higher pH to a lower pH, right? Even if you end up at a pH that's neutral, right? When we're talking about the change in pH, we're talking about whether or not it's becoming more or less acidic, right? Does that make sense, guys? I think that was a question on either the quiz or the lab, was you ended at pH 7
Yeah.
on one of the problems, and so I think that trips some people up. But it's about the change, right? What direction are you going? Other questions about that? Okay, and then for the pH of the solutions, right? You're always going to be given this pH equation, so you don't need to memorize that. If you were going from the pH to the molarity, you'd be given that version, right? So you don't need to have those equations memorized.
To be honest, this question totally tripped me up.
This one?
I don't know why the log, like I saw log and it just totally was like, oh God, log, I forget how to do it. So I had to remind myself a little bit about that.
If we go to the video, I can show you how to do it in the calculator, right? I have 2 different versions of calculators, so hopefully that'll get you where you need to go. But yeah, so any other questions?
Yeah, what's the one if you're going from the opposite problem? What's the?
I'll show you on the whiteboard. Remind me.
Okay.
Cool.
So highlight 14 and we'll go over that one.
Yeah. Okay, so this is one from the videos for acids and bases, right? So we have 2 different kinds of acids and bases, right? We have strong and we have weak. So there are 6 strong acids that you need to memorize, right? If it's not strong, then it's weak, right? Is everybody with me there? So what are the strong 6?
Hydrochloric acid,
Hydrochloric,
hydrobromic acid,
hydrobromic,
Sulfuric.
Nitric acid,
somebody says, was that nitric acid I got there?
nitric acid,
Nitric acid,
Sulfuric acid.
sulfuric acid,
hydroiodic,
hydroiodic,
perchloric,
and chloric acid. Was it perchloric?
HClO4,
Yes, you're right. Cool. Oops, sorry guys. Right, so those are your strong 6. If it's not one of those, then it's weak. Okay. So which of these are strong? Easier to say which one isn't strong.
acetic acid,
This guy, acetic acid, right? So this would be, oh, sorry, let me not do it the opposite of what the question's asking. So this one's strong, this one's strong, this one's strong, this one's strong, and this one is weak, right? Everybody okay with that? Cool. And what's the difference between a strong acid and a weak acid? Or a strong electrolyte and a weak electrolyte?
strong electrolyte dissociate completely,
That's correct. So a strong acid or a strong electrolyte will disassociate 100% or completely. And a weak electrolyte or a weak acid will only partially dissociate. Right? So between a strong acid and a weak acid, which one will have a higher conductivity?
Strong.
Strong. Why?
Because there's more ions.
Exactly. Does that make sense, guys? So when you have more dissociation, you have more ions, which means you have more conductivity, right? So that gets you to the next question, right? So a substance that dissociates completely into ions is known as a Strong electrolyte, right?
Yes.
Cool. If strong acid had been one of the answers there, that could have also been correct, right? Any other questions on that one? Cool. Number 17 is about titrations. So here we are talking about some of the language around titrations. So at the equivalence in a titration, the amount of acid and base are equal, right? This word equivalence might be used in a titration problem, right? But I don't want it to trip you guys up. That's why I want to make sure you guys understand what this word means, right? So the equivalence point is also known as the end point. Generally, those are used kind of interchangeably. If you're going on to organic, they're definitely going to tell you that that's not the case, but for now, we'll call them the same. Endpoint or equivalence point are when the amount of acid and base are equal, right? This is also known as the neutralization, right? Or should be around a neutral pH.
So it's what I'm in my brain, just when it gets balanced, when it's like at its easiest.
Mm-hmm. Yep.
Okay.
Yeah.
Did we go over titration in lecture? Or is that only from lab?
Just from lab. Yeah.
Okay, but we'll have titration problems on the exam.
You will, but they're not more, so like the solutions quiz, you had a titration problem on that one, right? So it's the only thing that you get into in terms of the language of the titration. There's a few like key words to understand, but I don't expect you to know all of those. But this particular one, equivalence point or endpoint, I think you should be familiar with. Does that make sense?
So
All of the other ones are really only relevant to lab, right? So an indicator is the thing that makes your color change when you get to the equivalence point. Titrant is just a fancy word for the thing that's in the buren. Analyte is whatever's in the reaction flask, right? So there's terminology around this, but it's not super important if we're not actually physically doing a titration. For the actual titration problems, the numerical problems, we should have enough to go on. Does that make sense?
So not so much figuring out a titration, just understanding what a titration problem is.
Right. Yes, and making sure that you understand the language of those problems. Did I answer your question, Sadie? I'm sorry, I kind of cut you off.
Yeah, no, you did.
Okay, cool. And you'll definitely have a titration problem on the exam.
What about like saturation point? I sort of remember going over that. Do we need to know that?
So what you should understand about saturation is just what can change the saturation, right? So temperature and concentration are the two basic functions of saturation, right? Does that make sense? That's as far as I need you to know about it. In a saturated solution, beyond saturation, right? You're not going to have a homogeneous solution anymore, right? You're going to have a heterogeneous mixture.
You said temperature and concentration?
Yeah.
Because of precipitate? Is that why?
It's not a precipitate because we're not doing a chemical reaction in this case, right? In a saturated solution, we just have so much stuff in the solution that we can't get any more to dissolve, right?
Oh, okay.
So a PPT is something that's formed in a chemical reaction, right? In this case, we're not forming anything new. We just have solid that won't dissolve, right? Does that make sense, guys? Cool. Questions? So I think we kind of went over number 18 already, right? What's the difference between a strong and a weak acid? I think this is one of the problems on either the quiz or the lab as well. Anyone want to chime in for me?
Just that one, the strong acid dissociates completely and the weak acids don't.
Exactly. Yep, you got it. Other questions about those? Cool. So number 19, what kind of problem is that?
I want to say it's a complex stoichiometry, but I think I'm
Stoichiometry, yes, definitely.
never going to be able to say that word.
No, it's okay.
Is it a gas stoichiometry?
Generally speaking, when I say gas stoichiometry, I'm thinking I'm going to need to use Pervner. Do I need to use Pervner here?
No.
Nah, right? So this is just a general or a simple stoichiometry problem. I hesitate to use the word simple with stoichiometry because I feel like that might make people angry. so yeah.
Well, it can get so much more complicated though. So
Yes, but you had a problem like this in the solutions quiz, right? So you've
this
seen.
looks scarier than it is.
Yeah, it's not too bad. Questions? We're okay. Okay, so number 20, this is a titration problem. The reason why I know that it's a titration problem is because the word standardized is used here. So those are the two main buzzwords that you need to understand from titration in order to identify this as a titration problem. Now, technically speaking, do you need to know that it's a titration problem? Not really. It's basically just a solution stoichiometry problem. It's just a particular kind of solution stoichiometry problem, right? So titration and solution stoichiometry are the same thing, right? It's the titration part of it is just the technique in the lab. Does that make sense? Anybody questions? You want me to say that again?
Can you just one more time? So thanks.
Yeah, so basically, all titrations are solution stoichiometry problems, but not all solution stoichiometry problems are titrations. Does that make sense?
Yeah, sorry. Yes, it does.
No, that's okay. That's well, we'll say it as many times as you guys would like.
My brain had like a blackout for a second.
Yeah, that's okay. I feel that way constantly right now.
And you just said, I mean, it's a titration problem, but we don't treat it any different.
You're not treating it any differently, but I just want you guys to be able to know that so that you guys don't get tripped up on words like standardization, right? So my goal is mainly, if you know how to identify a problem, then you're not scared of the language that's used in the problem, right? Then it's just, that's part of a titration problem. Does that make sense? So it's not super important that you know the difference between a titration and solution stoichiometry because there's no difference, right? But what I want you guys to be comfortable with is that some of the language of titrations is not generalized to solution stoichiometry, right? So standardization is a method that we use in titration when you don't know the concentration of a solution. So for example, sodium hydroxide is hygroscopic, meaning it takes water out of the air. So you literally, sodium hydroxide pellets are these little white pellets. And if you put them sitting out on a bench, then they will turn into little puddles because they take water out of the air. Because they take water out of the air, you can't get an accurate mass for sodium hydroxide. So you have no idea how much of what you're weighing out is sodium hydroxide and how much of it is water, right? So because of that, you make a solution and then you standardize it against something that you know the concentration of, or that you know the amount of, right? So that's what this problem is, right? Again, not important to being able to solve the problem, but helpful in not freaking you out, right? hopefully.
If we were actually in lab for this class, would we be doing stuff like this?
Oh, totes, yeah.
Hmm.
Yeah, it's a very unfortunate thing not being able to be in lab when you're doing chemistry, because that's pretty much the most fun part.
It makes me so sad.
I
It makes me so sad.
some students are like, yeah, go F yourself. That's not fun for me at all. But I love it. I think it's the most fun. It's like being in a kitchen, you know?
I was looking forward to
Some
lab.
people really like cooking, and some people are like, no, I'll go to a restaurant, thanks, you know? I personally love to cook. So this is, the lab is my kitchen. So
I was going to learn how to cook through your lab. No.
right. You can't eat what you make in the lab, so that part's less fun, but you get fancy colors and explosions, so that's like a close second.
I was looking forward to it.
But yeah, so these are all techniques that you would be doing in lab. Okay, questions about that one? We're good. Cool. This is also a general stoichiometry problem, but it's going backwards. So you're given the amount of product and you're asked to find the amount of reactants, right? I think there was something like this on the quiz as well, right? Does it freak you guys out when you start off with products and you go to reactants? Or are you guys pretty fluid with that? It's just the same steps, right? But flipped around. So you're still just going mass to moles, moles to moles, moles to grams, right? But now you're using the product to start and then ending with a reactant, right?
So is this 21 asking kind of multiple questions, or are you just putting these in here to give us an idea, the molar mass spots?
So for this practice exam was at one point an actual exam. So one of the things that I try to make students do is show me that they know how to calculate everything, right? You
Okay.
are pretty versed in making sure that you show me all of your work, but sometimes on tests, students will freak out and just not show work for one part, or they'll do like a weird side calculation and then erase it because it's messy. You guys are all in the habit of showing me all of the work all of the time, so I don't need to do this kind of stuff for you. But yeah, so that's why that's there.
Okay.
It's not like a secret thing that you need to know how to do. You
No,
guys.
I just thought you were helping us like lay out the information, which is kind of what that is. You're helping kind of organize the information of the model.
Yeah.
Okay.
So knowing that you're going to need to find all of these in order to solve the problem. And then the last one, did the videos go through percent yield, actual and theoretical?
I think so.
I don't remember that.
Yeah.
Briefly, I'm pretty sure.
I think it was
But just as a quick review here, the actual yield is what you find, what you're able to measure in the lab, right? The theoretical yield would be what you should get based on what you started with, right? So for example, if I have a theoretical yield of 2 tacos, right? But let's say along the line, I drop half a piece of fish or something like that. Then what I actually end up with is 1 taco, right? So that would be my actual yield. My theoretical yield would be how much I should be able to make, right? If I don't F anything up. But making tacos is a little bit more straightforward than doing chemical reactions, and the quantities are bigger and easier to handle. So in lab, it's much easier to lose some of the product. So that's why we have these terms, actual yield versus theoretical yield.
And then
Everybody okay?
You're giving us how to do it right there, aren't you? You just fill in the actual theoretical times 100, and that gives us the answer to that question, right?
Mm-hmm.
Will we have that if you, the equation on the exam?
Yeah.
Okay.
Yeah. Other questions about that?
Well, it's just about the praxis
Mhm.
exam in general. Would like the level of difficulty on this be comparable to the level of difficulty on the next exam? Or is it going to be harder? Because I just felt like this was pretty easy to get through,
Yeah. Yeah.
which I was kind of surprised with, and then I'm just concerned that it's going to be a lot. I should like prepare myself more for the
Yeah.
actual exam.
Yeah. Yeah. You're like, is it going to be like the solutions quiz? Is that what you're basically getting at? No.
Maybe, I don't remember that, but it
That one
could
was a
be.
little difficult.
It was basically like 100 years ago, right?
Yeah.
The answer is it'll be like this or easier.
Okay.
So
You were saying the last exam was the hardest part of the semester. So this exam to feel easier for us, I think, is because the last one was the difficult one. So this one feels a little bit lighter.
yes,
you know?
and there's just so much different material on the last exam, right? So there's a lot of different things. So you've got nomenclature, you've got Lewis structures. There's just a lot going on there. This exam is you have a lot of different units, but the basics are just dimensional analysis, right? And stoichiometry. And I've punished you guys with enough problems now that hopefully this looks easy. Whereas if, a month ago you had looked at this practice exam, you would have been like, wow, I hate everything and I want to die now. But hopefully I have tortured you thoroughly enough that you're like, this isn't so bad.
Well, it's good that we actually get it to the point where you can get through it easier. That means that we've learned a bit of chemistry.
Gosh, you guys, I can't even begin to expound upon how proud of you guys I am for making it to this part of the semester. Seriously, like, especially in this format, this is a hard class normally, and you guys are killing it. So you should feel really, really good about yourselves. And just give yourself a little mental reminder if you need to before this exam to really psych yourself up, and go look at that first quiz or the first exam and go look at the things that you did wrong there, and you're going to be like, oh my God, doy, right? But now you're like, well, whiz kid, I got this, right? So you should feel really good about where you're at with this stuff for sure.
You've helped us understand it though, Teach. I mean, the way you teach definitely has a big part of that.
Thanks, guys. All right. So